Chapter 6, Acids and Bases. Alright, so this part of our unit here is dealing specifically with acids and bases, as the name maybe suggests. And we're going to get into more depth than you have gone with acids and bases before. Just start off, there are a couple things we commonly use acids and bases for. Sometimes we'll put lemon on fish because the fish maybe tastes too fishy, or maybe we just like the flavor. The fishy smell of fish, some of that comes from bases. And then so by adding lemon, which is an acid, we actually neutralize those and kind of kill some of that fishy smell and flavor. If a drain is clogged, we use a strong base. That strong base helps to dissolve it actually chemically reacts with the fats. And that's actually disgusting thought here. Most drain clogs, according to plumbers, are due to large chunks of grease and hair, and bases will cut through the grease, fatty parts, and make it so everything else can move along. A wart, we sometimes can use acid to remove it. There's other ways to do that. If you have acid indigestion, often you consume a tablet that has a base in it. Now, you should theoretically remember how to name acids and bases. We've done a bit of review with this already. But just to show you, your notes booklet in front of you, if we were to take a look at the name of our acid, now we can name acids two ways: as an acid or as a hydrogen something compound. So if we have hydrogen, for example, iodide. Okay. This becomes, we drop the "ide," and I made that a little bit longer than I needed to. Iodide. There we are. We drop the "ide" at the end, and it becomes a hydroic acid. So this top one here, this is basically, there's 4 of these: hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide are the 4 common ones. There's another goofy one, is hydrogen cyanide, and they all become a hydroic acid. So this particular one here, hydrogen iodide, becomes hydroiodic acid. Okay. Hydrogen chloride would become hydrochloric acid. Hydrogen cyanide would become hydrocyanic acid, and so on. Now, if the compound name would be hydrogen, let's say, sulfate, so we can drop the right way, lovely. This becomes, and this one is a little bit goofy, just it sounds better, sulfuric acid. Okay, if it's something else that ends with ate, hydrogen acetate becomes acetic acid. Hydrogen chlorate would become chloric acid. Hydrogen perchlorate would be perchloric acid. Okay, and then we have and then the other kind of compounds that are acids could be hydrogen something ite. And so maybe we have hydrogen, and you can look in your table of polyatomic ions, right? So you look in here, and anything that's got an ite in it, nitrite, sulfite are the 2 common ones in here. And with either of those, chlorite, there's another one, hypochlorite. With either of those ones, so let's say we have chlorite here. This becomes chlorous acid. Okay, if it was hypochlorite, it would be hypochlorous acid. Okay, So naming acids is something you do have to be able to do. You have to be able to figure out if I have sulfuric acid, okay, that's hydrogen sulfate, so then that's going to be H2SO4. If I have chlorous acid, oh, that's going to be hydrogen chlorite, that's going to be HClO2, okay, and so on. Bases, on the other hand, are very easy. You name the metal ion and then you say the word hydroxide. So for example, if I have KOH, this is a base, potassium hydroxide. Okay, name the metal and then hydroxide. Okay. You can do this with anything. MgOH2, magnesium hydroxide. NaOH, sodium hydroxide. Okay, this particular one here, potassium hydroxide. Okay, so that's in terms of naming. Very brief review. I have some more review stuff we can do as a group or individually if you need the extra work with those. What about their properties? Again, this is, or should be, hopefully, review from Science 10. Acids and bases. Well, acids will turn litmus paper red. They have a pH less than 7. They conduct electricity, which means they're an electrolyte. They will react with metals, such as magnesium or zinc, and they produce hydrogen gas. If you were to taste them, they would taste sour. Generally, we don't recommend tasting things in the lab. That being said, if you have food that tastes sour, it's because of the presence of acid in it. In terms of if you get some on your skin, generally they have no characteristic feel. When we get to bases, we'll say that they feel slippery. That being said, even a weak acid, something like lemon juice, or really dilute vinegar, if you have a small cut or like a hangnail or something like that and it gets in there, you will definitely know that it's there. I guess that would be a characteristic feel. Bases turn litmus paper blue. They have a pH greater than 7. They also conduct electricity, which means they are electrolytes. They do not react with metals to form hydrogen gas. In general, they don't react well with metals. There's a few metals they will react with, but they will not form hydrogen gas in those reactions. If we were to taste them, and again, don't taste stuff in the lab, but if you're tasting food that tastes bitter, it's because it's a base. Bases also feel slippery to the touch. Reason for that actually is that they are saponifying, which means they are making soap out of some of the phospholipids in your skin cells. If you think about your cell membrane as a phospholipid bilayer, back to Science 10 again, that saponification reaction is making some of those lipids turn into soap, and there's that chemical reaction. Bases therefore feel slippery because you're turning some of your skin into soap. Sort of a disgusting thought. Alright. That was sort of review. Now moving on to a little bit more new stuff. Alright. So, as you can see up here, these are some of the outcomes from the Alberta Education Program of Studies. Okay. Now, we're going to start off not by using the modified description of acids and bases. We're going to start off with what Arrhenius actually came up with first. Alright, so Arrhenius acids. He said that the characteristic of an acid is that it ionizes in water to form hydrogen ions, or to produce hydrogen ions. Okay? This is different than an ionic compound which dissociates. This has to be some sort of a reaction. Okay? Because an acid is a molecular compound and it's actually getting broken into two pieces. It's getting broken into the hydrogen ion, and then it's getting broken into either one of these polyatomic ions, or it's getting broken into a non-metal ion. So there's going to be a hydrogen ions, and there's going to be some kind of anion. Okay. Now, according to Arrhenius, H plus ions identify the solution as an acid. So H plus equals acid, according to Arrhenius. Therefore, the higher the concentration of hydrogen ions, the more acidic a solution will be. So the question, of course, I already sort of touched on this. Acids are a molecular substance. Why do they conduct? Molecular substances, we've learned in the past, don't conduct electricity. They don't have any free ions. The free electrons. The reason is this: the ionization. An acid forms ions in water. Okay, and so we have hydrogen chloride gas in the presence of water, according to Arrhenius, is going to make H plus, and it's going to make chloride. Okay, this is an Arrhenius acid. This is how we've defined acids up to this point. An Arrhenius base. It dissociates in water. Okay, so this is the ionic bit to produce hydroxide ions. The presence of an OH minus ion identifies the solution as a base. Higher the hydroxide ion concentration. Okay, now this is maybe new. These square brackets around an ion means concentration. So the square brackets, if you put them around something, means the concentration of whatever's inside. Okay. Concentration of, oh, that's going to be hard to see. I'll make it smaller in a second. Whatever is inside. Okay, so that's what we have when we're looking at those square brackets around something. You're going to see this often from here on in. Square brackets around something means the concentration of whatever's inside. Okay, so the higher the hydroxide ion concentration, the more basic the solution is. Almost all bases are ionic, and therefore they conduct electricity. Now, dissociation is the term given to a species that separates into its ions when placed in water. Okay. Ionization, for all intents and purposes, looks very similar, but according to Arrhenius, it has to be different, because, again, molecular compounds don't dissociate. Okay, something's happening, and so he said, no, we're going to call this ionization. You have to know the distinction between ionization and dissociation. Okay, so sodium hydroxide will form sodium ions and hydroxide ions. All right. Now, because of that issue right there, the ionization bit, how is it different than dissociation, other than, well, obviously something different's happening because it's a molecular compound? Arrhenius said, okay, let's add water as a reactant instead of assuming the reaction occurs in water. As a result, we take hydrogen chloride, which is dissolved in water, and it reacts with more of the water. And now this H from the chloride goes to one of the lone pairs on the oxygen. We end up with H3O+, which he called a hydronium ion, as well as we're left with Cl by itself, a chloride ion. A modified Arrhenius acid, that's what we're going to be using as our Chem 20 definition. It reacts with water and it produces a hydronium ion in aqueous solution. Okay? The hydronium ion identifies the solution as acidic. Now, there is actually evidence people have come up with. Actually, if you're curious about this, Wikipedia has a pretty good in-depth article on this one that, last I checked anyways, was fairly accurate. Okay. Evidence showing that H plus ion does not exist by itself, but they're always found as hydrated. Which means it's formed into a hydronium ion. Okay. In this case, they bond with water molecules and form this thing called a hydronium ion. A modified Arrhenius base reacts with water to produce a hydroxide ion in aqueous solution. Okay, so we're going to be using both definitions of Arrhenius bases. Both the original one, where we can talk about dissociation, we can also talk about this reaction with water. And what this does is it makes the range of substances that are bases, it makes them bigger. There's more things now that are bases. Okay. Once again, the presence of a hydroxide ion identifies the solution as basic. So, what do we have here? An aqueous solution of hydrogen iodide. I'll show you with the first one here. Okay, so we have HI. What I'm asking you to do here is let's write out some let's try that again. Ionization equations. Okay, to show how these things are acids. This is one of the things you're expected to do. Is if I tell you, first of all, we've talked, and we'll talk in more depth about strong acids, strong bases. If you have a strong acid, it reacts with water completely, and we'll get to the completely bit later on, and that's going to form a hydronium ion. It's going to be aqueous, and it forms an iodide ion. Aqueous solution of hydrogen nitrate or nitric acid. Again, same kind of an idea. HNO3 aqueous will react with water. And that's going to form a hydronium ion. That's our H3O plus. Plus a nitrate ion, NO3 minus. Right. Now, an aqueous solution of lithium hydroxide. This will just be a regular old Arrhenius base, because we put this, let's make that L so that it's readable. We put this into water, it will dissociate. We end up with lithium ions and hydroxide ions. Ammonia is an example of a modified Arrhenius base. According to Arrhenius's original theory, ammonia is not a base. Empirical evidence would suggest if we dissolve ammonia in water, it has all those characteristics of a base that we talked about way up here. It turns litmus paper blue. It has a pH greater than 7. It conducts electricity. I would recommend against tasting it. I suppose it would taste bitter. It would feel slippery. And so in this case, what we would have to show is that ammonia as a gas, actually, we'll talk about getting it into water in a moment. It's telling you it's an aqueous solution of ammonia. We'll leave it there. Is going to react with water. Now, in this case, it's going to produce a hydroxide ion. Oops. What that means is it's going to yank one of these H's away from the oxygen. And so it's going to make NH4 plus ammonium. and hydroxide. Which means it's going to be a base. Now, if you'd rather write H2O instead of as H2O, you could write it as HOH. That makes this maybe a little bit easier to envision. Because this particular H then gets removed, goes to the NH3, and we're left with just the OH minus. Okay. Now, we need to distinguish between the concept of strong and weak acids and bases. And part of this discussion has to be the fact that if you have different acids, even if they have the same concentrations, they can have different properties. Okay? And so take a look on page 218. Like, actually do it. There's a lovely picture at the top. Like, flip there in your textbook and look at it. Right now. Yeah, do it. Okay, you can pause this and then do that. Lovely set of pictures showing the reaction between magnesium, metal, and hydrochloric acid with 2 concentrations, and acetic acid with 2 concentrations. Right. Now, explanation for that result of the fact that 1 mole per liter hydrochloric acid reacts pretty vigorously, as does acetic acid. But then we look at 0.1 mole per liter hydrochloric acid compared with 0.1 mole per liter acetic acid. There's a huge difference there. So from the Arrhenius theory of acids and bases, and the modified theory actually, all acids produce hydronium ions in water, all bases produce hydroxide ions in water. But not all acids ionize to the same degree. This is important. If we look at that set of pictures, I should say, on page 218, which if you haven't gone there yet, do it now. If you look on there, hydrochloric acid and acetic acid, or ethanoic acid, both of those two ionize to different degrees. There's more of a reaction going on with hydrochloric acid, which means it must be ionizing more. Right? Now, strong acids are the only ones that ionize 100%. The reactions of strong acids with water will be written with a quantitative arrow. Quantitative is a nice straight line arrow. This is the kind of arrow you've been using like all the way through chemistry up till now. And this quantitative arrow means that the reaction goes 100% to completion. There are only 6 strong acids, of which I have written 5 of them. Okay, if you're wanting to look for the other one in your data booklet, go towards the end. In fact, they're all there. They're on this page. It says 8 here. We have perchloric, we have hydroiodic, we have hydrobromic, we have hydrochloric, we have sulfuric, and we have nitric. So as you can see, the one that I missed here was HBr, hydrobromic acid. Okay. These things are going to react. We use this lovely quantitative arrow here to show that they react 100%. Hydrochloric acid, for example, will ionize completely. We'll end up with hydronium ions and chloride ions. When we look back at the solution, all of this is used up. It's all turned into this and this. Weak acids are different. Weak acids react very little with water, and only a small percentage of acid molecules will actually form ions in the water. Long and short of it, they do not ionize 100%. Now, these acids are said to be at some constant equilibrium. Okay. Much more about that in Chem 30. All acids are considered weak except for these 6 strong acids. So if you have an acid that is not one of these, it's a weak acid. Doesn't mean to say, and I'll make this distinction many times, it doesn't mean that it's not concentrated. It doesn't mean that it's not dangerous. Some weak acids are very nasty things. But we call them weak acids only because they don't ionize 100%. Right? You can have a very concentrated solution of a weak acid. You can have a 12 mole per liter solution of some weak acid. It would probably dissolve your flesh if you bothered to stick your hand into it. But it's not a strong acid only because it's not one of these 6 up here. It doesn't ionize 100%. And so with these weak acids, instead of using a quantitative arrow, like that one, we use equilibrium arrows, where we have half an arrow going both directions. Okay? We can use these to show what direction the equilibrium is more in. So instead of drawing full ones like this, I could show that it mostly goes to the right-hand side, like this, or I could show visually that it mostly is on the left-hand side, that the reaction proceeds forward very little, like this. Okay. Once you get to Chem 30, and we're going to talk about it here this year, but we're not going to worry about it too much. Alright, so how does the identity of an acid affect its acidic properties? Okay, well, specifically with some math here, 0.1 mole per liter of a strong acid has a higher concentration of hydronium ions than does a 0.1 mole per liter solution of a weak acid. Which means strong acids react more vigorously and they are going to be better conductors. So if you have 2 things and they're both acids, one of them is a great conductor of electricity and the other is a terrible conductor of electricity, then you can right away say, oh, the strong acid is the one that reacts more vigorously. Or you could say the strong acid conducts electricity better. Okay. What else do we have here? Well, we can also look at non-metallic oxides. Okay? Carbon dioxide is a weak acid, or it can form a weak acid, I should say. So when carbon dioxide reacts with water, it ionizes in a 2-step process. Okay, this does not mean it's dancing to country music. To form hydronium ions and hydrogen carbonate ions. Step 1. It reacts with the water. Okay, CO2 plus H2O, and we end up with H2CO3. Yes, you have to know how to do this. Step 2. The H2CO3 reacts with water. Now, it doesn't react completely. This, you'll notice, is a quantitative arrow. This second step, we use an equilibrium arrow. Okay, I'm drawing them both the same way. I don't know off the top of my head how much this reaction proceeds. I'm just going to show that it doesn't happen 100%. And it's this second step that shows that, yes, this is in fact an acid. So carbon dioxide will form this H2CO3 in water. It reacts with water to make hydronium ions and hydrogen carbonate ions. Okay. So how do we know what is a strong acid? It's on this list. How do we know what's a weak acid? Well, once again, weak acids are an acid that's not on this list. Now, how do you know something's an acid? Well, usually an acid will start with H in its formula. or end with COOH. Okay. We've got one more thing we have to add to this. Acids can also be non-metallic oxides. Non-metallic oxides generally will react with water, and then they will form a weak acid. Okay, so you got to be on the lookout for non-metallic oxides as well. All right, a strong base, 100% dissociates into ions in water. The reactions of a strong base with water will be written with a quantitative arrow. A strong base such as magnesium hydroxide has a very low solubility in water. But the small amount of these compounds that does dissolve, it dissociates completely. Okay. In terms of their formulas, all strong bases have the hydroxide ion present. They're easy to pick up on. Something hydroxide, yep, it's a strong base. Okay. Weak bases, okay, they react very little with water, and only a small percentage of the molecules will form ions, which means only a small percentage dissociate. They're said to be at equilibrium. They do not have 100% dissociation. So when I wrote out up here, this arrow, I knew full well that this arrow is not the right arrow. I should have gotten rid of this arrow, and instead of this arrow, I should have used an equilibrium arrow. And so we're going to fix that down here. This needs to be an equilibrium arrow. Right. So bases can be strong bases, anything with hydroxide. Weak bases react with water to form hydroxide ions. And finally, oxides. Okay. Now, a non-metallic oxide, highlight that. Non-metallic oxide forms acids. Non-metallic oxides form acids. Metallic oxides form bases. It's 2 steps again. Okay, so carbon dioxide, let's look at that one again. We did that before. You can do carbon dioxide again. I'll do one more for you. Let's look at what about nitrogen oxide, NO2 gas. Okay. Well, this will react with water. It's going to do a few things in water. The part that we care about okay, I'm going to balance it here already. This is going to make me, excuse me, sorry. H 3 and it's also going to make me I believe nitrogen monoxide. Nitrogen dioxide, I wrote this down without thinking, is a little bit challenging. Now it's going to react with the water, and we will end up with, we need to have 2 of these. I put the 2 there. It actually needs to, I believe, be a 3. Yep, there we go. Okay. This is the important part. Ah, this is a strong acid. HNO3 reacts with water to form, and this is a strong acid, so we have to be on the lookout for that. This is going to react with water. And this is a very quick reaction. Okay, so it's not like it's kicking around for a little while in solution as HNO3 kind of hanging out and chilling until it runs into some water. It's in water, so this happens fast. This will make hydronium. You'll notice I'm writing all these subscripts. You need to do the same when you're writing this stuff down. In fact, this one here, this nitrogen monoxide, it can also react with water. And we end up with a variety of different acids out of that whole deal. That being said, this is our step 1. This would be our step 2. Now what about a metallic oxide? So non-metallic oxides form acids. I've said this about 8 times. It must be important. Metallic oxides will react with water to form bases. So let's look at this one. So we have Na2O as a solid. It's going to, first of all, dissolve in water. It's going to make 2 Na pluses. And it's going to make an O2 negative. This is the important bit. As soon as you see this oxygen that in the form of an oxide ion, O2 minus, aqueous, will react with water. Okay, this will be in equilibrium. You do not have to predict how far along it will go. You just have to know that it does make a base. And we're going to end up with actually OH minus, because this grabs onto the oxygen here with the 2 minus charge, grabs onto one of the hydrogens. Okay, so again, if we wrote this as HOH instead, one of these hydrogens goes here. The other one, oh, we've got another hydroxide. So we actually end up with 2 hydroxides out of this whole mass. So metallic oxides are going to form a base. Non-metallic oxides are going to form an acid. So we're looking, metallic oxide, that's going to be a base. Non-metallic, oh, that's going to be an acid. In summary, strong acids have greater acidic properties than weak acids. Stronger the acid, the greater the concentration of hydronium ions. Stronger the acid, the lower the pH. Concentrated acids will have greater acidic properties than dilute acids. The more concentrated the acid, the greater the concentration of hydronium ions. The more concentrated the acid, the lower the pH. Okay? So I'm kind of distinguishing here between strong and concentrated. Summary of bases. Strong bases have greater basic properties than weak bases. Stronger the base, the greater the concentration of hydroxide ions. Stronger the base, the greater the pH. Concentrated bases have greater basic properties than dilute ones. The more concentrated the base, the greater the concentration of hydroxide ions. The more concentrated the base, the greater the pH. We're stopping for right now. Now, I've already skipped over some of these, but you need to work on page 226, questions 3 and 4. And then if you scroll up, or, well, you don't have to scroll, I will scroll. Page 217, questions 1 to 5. Those need to get done. So if you can work on those right now, that would be awesome.